Hi, in this video, we want to take a look at fixed effects and random effects in mixed effects models. Okay, so I'm going to just dive in. I think it's the best way to go. All right, so here we're going to look at a simple example of random effects. All right, so we're going to be working through the library for NLME. So it's the NLME package, pretty standard in R we're using. Now, the first example is going to use the rail data set, which is in the package. And here's the data. Okay, so we can see that we've got travel time and we're modeling it as depending on which rail we're on. Okay, so one thing that we would it would be very natural to do would be to take like the average time along each rail, because that's all the data we have. We have nothing else to base it off of, so our only predictor is rail. Let's just take an average, all right? Well, let's see how things work out. All right, so what we're going to do, we're going to make a mixed effects model. So the LME gives us mixed effects. Mixed effects means we have a fixed effect and we have a random effect. Okay, so what's going to happen? See how I have rail over here on the right of the conditional line? Okay, so each group in the rail data set, in the rail field, is going to get like its own equation. Now, the stuff that's over here on the left of that bar is going to be the coefficients that vary from group to group. So random effects means the variables, the coefficients listed here are going to vary from group to group. Fixed effects is that whatever is up here is going to be fixed. It will be the same for all individual groups. Okay, so let's take a look. So here, for each rail group, we're going to have a different intercept. Okay, that's what the 1 means, because that's the constant, remember? Now, here it's redundant. It's going to end up that since we have the 1 down here, like having it in the random position trumps it in the fixed position for this argument. All right, so we can see that if I do this, the intercept for the number 2 rail is 32, then we have 50 for the 5th rail, then 54 for the 1st rail, and 96 for the 4th, which is the largest. Okay, well, let's take a look at this. So if I hit summary on a mixed effects model, we get the AIC, the BIC, the log likelihood. All right. Now, I'll also get random effects information. What it's going to give, it's going to give me like standard deviation information and residuals. That's what it's going to tell us. Now, for the fixed effects, what it's going to do, it's going to go through and do hypothesis testing. So by default, this is what it gives. And then we'll get the within group residual. So that's important. It's within group. So this is within each rail group. What are the residuals? And then it treats all the residuals as, it throws them all into like one big bucket. And then we get some information out. All right, well, we can plot it. And what it'll do, it'll take the fitted values, and then it'll take the standardized residuals, and it'll give us some information. And we can see that we know that each of the rails has the same fitted value. So we know that these 3 correspond to one rail, and so on. All right, so if I want to do hypothesis testing, or sorry, confidence intervals, if I want confidence intervals, I just use the intervals function and I just put in my model. All right, so for fixed effects, it gets the lower and upper bound and estimated value on the intercept. Now that is the overall intercept. Okay, and then for random effects, it gives me an estimate on the standard deviation. Notice that it's not telling me about the individual coefficients, it's telling me about the standard deviation aspect. And of course, we got a lower bound, upper bound, and an estimate. And now here's the within group standard error. So remember, within group, this is within each rail. And we can run ANOVA. And the ANOVA It's just checking to see, effectively for this one, it's checking to see, is the intercept, the fixed effects overall intercept, substantially different from 0? And of course it is. Everything was bigger than 0, so you know, unless we got something really weird going on, it's going to be that way. All right, so now there are two major ways to fit our models. We have the REML and we have ML. ML is maximum likelihood, and REML is restricted estimate maximum likelihood. Don't get mad at me if I messed up the RE, but it's I think it's restricted E maximum likelihood. All right, so maximum likelihood doesn't perform as well when we have small data, and REML performs better when we have small data, and when we have big data, they're about the same. So there's really, I don't really see an advantage of using maximum likelihood over the other. I'm sure that there's, in some situations, there's an advantage. I don't know about it. Do what you feel is best. Do whatever you feel comfortable with is probably what I should say. And do whatever your audience will accept and agree with, because a statistical model that is simple but accepted is far superior to a statistical model that is super slick but doesn't get used. All right, and we get our AIC, BIC, and our log likelihood. Now, one thing you'll notice is that if I use the maximum likelihood fit or the REML fit, they're going to be very, every time I've looked at it, they've been very close to each other. You will get a difference, but I don't see, you know, a huge difference so far. I would just go with REML unless you have a good reason not to. All right, so that was a simple random effects. Let's look at a randomized block design. Okay, so now what we've got a subject. So like here we have subjects 1. This is when they did like type 1, type 2, type 3, type 4. Now what are the types? I don't know, but it's talked about ergonomic stool. So I'm sure that's the type of stool and the subject testing them. So here's the scores for subject 2 with each of the different types. And here's the effort that they put in. And we go down the list. All right, so we notice that here we've got subject and we've got type, and then we have effort. All right, so every time I'm looking at this, I know that all of my measurements are kind of like contained within the subject aspect. So if I'm a subject and I sit down 4 times, I am a common aspect to all 4 of those observations. If you are a subject and you sit down the 4 different types of ergonomic stools, all those informations, all those measurements are like connected to you. Because they're all connected to the individual subject, we want to group everything by subject. So a good rule of thumb is wherever we think there would be like hidden variables lurking around, that's the variable we want to group on. All right, so my model for this one is going to be mixed effect. It's going to be a mixed effects model. We're going to have fixed effects and random effects. For random effects, we've got a subject, and we're going to go ahead and for each subject, we're going to say that there is a different intercept, a different constant in the model. And then we're going to say for the type is going to be constant across all subjects. So all subjects, so each subject gets their own equation. So by putting subject here, I'm saying I want each subject to have their own equation. I want the y-intercept to vary for each subject, but I want the type, I want the coefficient for type to be the same for every single subject. Okay? All right, so when you start digging into these, the first thing you really want to look at is the coefficients, because the coefficients tell you or make it more clear what your model is when you do this. Let's take a look. All right, so remember that type is a categorical variable. So type is going to be like a dummy variable situation. And so here I have the dummy variable coefficients, and you'll notice that they're the same for each of the types. And the baseline is for type 1. All right, so now the intercept is going to be what's going to vary. So because I put the constant here, the intercept is what changes for each individual one. All right, now let's look at the summary of it. All right, so AIC, BIC, log likelihood. Here's our formula. So remember, for random effects, for that part of the equation, it just gives us the standard deviation information. For the fixed effects, it goes ahead and does hypothesis testing for us, and it goes ahead and spits out some correlation. And so this will be the correlation between the measurements for each individual subject. And then here I can run through a ANOVA for hypothesis testing also. All right. Let's go ahead and plot it. All right, so now you'll notice I put type P residuals, that means it's Pearson, and they're depending on the fitted, and we're grouping by the subject. By grouping by subject, you'll notice that each of the scatter plots correspond to a different subject. Now, let's look at this. Remember 7 and 4, when I scroll up, all right, here we've got subject 7 was the first one. Subject 4 was the last one. So here we can see the intercept is 7.7, and here we have 9. So let's look at this again. And so this gives us residual plots for each of them. And these look like clouds. Now, there aren't very many points, so it's hard to detect a pattern. But, you know, we've got a good amount of information on this. All right, now, how are things going to change if I take the constant out of the fixed effects? All right, so if I look up here, you'll notice that I have intercept in the fixed effects. Down here, what I'm doing is I'm saying do not include the y-intercept in the fixed effects. This means that the intercept is always in the random term, the random effects aspect. All right, well, you'll notice that, first of all, the order changed, but also the values changed. But wait, there's more. Because the coefficients are not the only thing being estimated. Also, variance and standard error aspects of the model are being estimated also. And so by changing the order on things and changing the arrangement, changing the layout, even though if I was to write down the equation, they would look very similar to each other, I'm getting actually different models because my estimated variance is going to change and my estimated coefficients are going to change. When we do mixed effects models, order matters. Remember that order matters when I do this. So if I change in where I put them, where I place them, if I have multiple variables in the grouping aspect, the order of the variables matters. All right, well, let's keep going. All right, so here the random effects is on the coefficient or on the y-intercept. Gives us some information. Now you'll notice that the intercept was completely dropped from the hypothesis testing, but we did pick up the type 1 dummy variable. All right. And you'll notice that the correlation now is constant. Where the correlation varied before. Kind of interesting, right? So that should show you that all of our variance, covariance, and standard error estimates all change depending on how I lay it out. And so it's, even though it will look like the same model when I write it down with pencil and paper, it's not. It's deceptive. So when you look at mixed effects models, the big thing I want you to walk away with is, number one, each group gets their own equation, and the random effects tell us how it changes. Fixed effects is constant across. The last thing I want you to remember is that how I specify things changes the variance, covariance, and standard error estimates. So a lot of times, especially in the social scientists, you'll start reading about like fixed effects, random effects, mixed effects models, and they really won't specify what it is that they're doing. And I always question, do they actually understand the fitting of the parameters and the estimating of variance, covariance, and standard error? All right, let's look at mixed effects models for replicated block design. All right, so here, we're saying that score depends on machine, and we're saying that my grouping is on the worker, and we're going to say that each worker gets its own y-intercept. All right, so when I build this model, I can see that the intercept changes by the worker, and I have dummy variables on different machines. Okay. Now, what if I change this up? What if I was to say workers and machines are the grouping variables? Now, when I do worker slash machine, that's different than machine slash worker. That's an important point to make. So even though like on pencil and paper, if I start writing out like the coefficients of it, not the actual values, but if I start writing out like, you know, betas and alphas and x's and z's and stuff like that, in equation presentation, it will look very similar. It's not. All right, so let's see how that changes. All right, so when I do worker then machine, you can see that here, these correspond to worker 6, and then machine A, machine B, machine C. This corresponds to worker 2, machine A, machine B, machine C. And we're saying, when we do this, we're saying that the coefficient can change on each one. Now up here, the intercept only depended on the worker. Now it depends on the worker and the machine. But something that's interesting to note is that either way, since I have machine and fixed effects and not in random effects, I get machine B, machine C in both models. And machine B, machine C are dummy variables, of course. And of course, we can do hypothesis testing to see if they are equally informative. All right, so now let's go back to our ergonomic stool example. Now what I want to do, actually, let me scroll up. I did not print out the summary, okay. And, all right, so here I want subject and type to be the grouping variables. It goes subject, then type. I want the intercept to change by group, but I want the type coefficients to be constant across groups. And so here we can see how this works out. So each of the 4 we have a different intercept every single time. All right, let's do this again, but now we're going to go through and we're going to say that age, which is going to be a numeric variable for this one. So far, we've always had categorical, and then I'm going to have sex and subject. So age will have a constant coefficient across all groups, but the intercept will vary. And now this is different than getting like the same format for a linear model, because a linear model will have a different standard error estimates. And so here are the equations we have for each of these, and we can see that how these work out. Now, something about this, when I hit the summary, you can see that this tells me that we're doing subject within sex. Okay, so if I group up my subjects, or if I take all my observations, should I put them into sex and then, you know, identify them as subject, or should I go subject, then identify by sex? Well, if I'm grouping them up together, I want to say that sex is like the grouping, the bigger grouping variable. So here, this tells me, and did I get the right order when I made this? All right, so when I was writing up this example, I actually had switched. I checked right here, and I saw, hey, I had sex in subject. I knew I was wrong, so I went back up and I changed my code. So here, sex is like the first grouping variable, then subject. Now for our random effects, it gives us a standard error information. Then we get our hypothesis testing on the fixed effects. And then it'll tell us the correlation. You know, across the groupings. All right, now for our next one, we've got dog, we have side, we have day, and we have pixel. Now, what does pixel mean? I don't know. Don't really care. It's just data for me to work with. All right, so what we're going to do, we're going to build a random effects model. I've got pixel depends on a quadratic model on day, and we're going to let day vary across dog, which is kind of a funny thing to say, and then we're going to let the y-intercept vary across side. Okay, let's look at how this works out. You'll notice that here, everything is set up, you know, so that, you know, my, like the dog is the grouping variable for day, and the side is the grouping variable for the y-intercept. Before, we only had one grouping variable, and that was for all coefficients. And we can see how things vary across. All right, now let's change this up. Let's say that I just want day to depend on dog. Then I want the coefficient, or sorry, the y-intercept to depend on dog and side. Then I want, oh, this is my fixed effect. I want to add side to my fixed effects. So let's take a look at how my models change. So here we can see that on the original model, the quadratic term is the same. Day varies, and the intercept varies by the grouping variables. Remember, there's two different grouping variables. And we're saying that side is within the individual dog grouping. Now here, we can see that day is varying by subject, and then the intercept is also varying with that. If I don't put in a 0 into like my random effects, it'll usually pick up varying the y-intercept for us. Now here, we can see that we've got the quadratic aspect. We have the degree 2 term, the degree 1 term are constants, but my y-intercept changes by which dog and which side we're looking at. Now here, we can see that we have the side term in fixed effects is constant. The quadratic in for day is constant, but day, the linear term changes and the intercept also changes. And if I try to do ANOVA on this, objects with different fixed effects, the comparison is not meaningful. So watch out for that. That mainly just said, that really what that's saying is that we can't trust the p-value. But if I see that I have large likelihood ratio, then it's probably okay. You just can't trust the distribution. All right, well, that's all I've got for you. Take care and goodbye.